So section 2.1 is discussing quadratic functions. So you already know what a quadratic function is. You know that it's a polynomial with the highest degree of 2. What this is going to make is a U-shape. You've already graphed the parent function for a parabola, so you already know that the parent function has a vertex at 0, 0. This graph right here is called a parabola. It's the graph of your quadratic equation. This equation was y equals x squared. It was the most basic we could get. The a value is the coefficient of x squared, so in this case it's just 1. When the a value is positive or greater than 0, it's going to open up just like you see here. If you reflect it over the x-axis, you negate the entire thing. So if you reflect it over, do you see that it's going to be opening down? So if the a value is greater than 0, it'll open up, right? Greater than 0 is a positive number, positive people smile. A is less than 0, that's negative values, negative people frown. See how it looks like a frown? So if you have trouble remembering it, try to think about that. The vertex is the turning point. So if it opens up, if your a value is positive, your vertex is that turning point right there. That would be considered a minimum value because you don't go below that. If you are opening down, if your a value is negative, your vertex is called a maximum because you don't go above that. The vertical line that passes through the vertex, that's called your axis of symmetry. See how you can fold your paper along the axis of symmetry and end up with the right-hand side of the graph? Same thing over here. It's the vertical line that passes through the vertex. Here's a quadratic equation in vertex form, sometimes called standard form. The HK is going to be your vertex, that's your turning point. Your graph is going to have an axis of symmetry at x equals the x-coordinate of the vertex, which is considered h. If a, so a is out here this time, if a is positive, you're going to open up. If a is negative, you're going to open down. So that's similar to before. When it's in this form, you can see the transformations rather quickly. Remember the vertex is h, comma, k, so you take the opposite of what you see here, so you get 4, comma, keep the sign of what you get here. So your vertex is going to be 4, 1, which means your axis of symmetry, I'll abbreviate it as AOS, axis of symmetry, or vertical axis it's sometimes referred to as, is the vertical line. Well, how do you write in a vertical line? Well, it's going to be x equals a number. What is that x value equal? It's usually x equals h. So what is the x-coordinate of the vertex? 4. So your axis of symmetry is x equals 4. Will you get points off if you do not write it as an equation? Yes, you will. So be very careful. Make sure you write it as an equation. Will this parabola open up or down? Well, that depends on the a value. The a value in this case is technically just 1. So it's going to open up. So the shape of it should look like this. Now, I want to know, where is this graph increasing? Where is the graph decreasing? I'm going to want to know the domain, the range, and the intercepts. I highly recommend finding the increasing, decreasing, and range intervals once you're finished graphing. So to help us graph, I want a few extra points. So I like to pick a few points to the left and right. So we already know 4, 1. So maybe let's pick a point to either the left or right. We know the axis of symmetry occurs here, and we're going to use that to help us find some more points. Would you rather plug in a 3 or a 5? Most students would rather plug in a 3. If you substitute in 3 into this equation, 3 minus 4 is negative 1. Negative 1 squared is 1. 1 plus 1 is 2. So you have another ordered pair here. 3, 2. Which means if you reflect that over the axis of symmetry, that's 1 away, so it has to be 1 away over here. So you also have the ordered pair 5, 2. And you can always feel free to plug that in and get 2 as your output, or you can use the line of symmetry. So let's try another ordered pair. I want to see exactly what this pattern is going to be. So I'm going to try to substitute in 2. I could have chosen 6, but 2 and 6 should have the same exact output. When I substitute in 2 into this equation, 2 minus 4 is negative 2. Negative 2 squared is 4. 4 plus 1 is 5. This is 2 away from the axis of symmetry, so you're going to also have the point 6, 5. And then you're just going to connect it with a nice smooth curve. Now, just by looking at this graph, you should see that there are actually no x-intercepts, right? Your parabola never intersects the x-axis. So I know right away that this should be none. But how do you figure that out if you don't have the graph? Well, you substitute in 0 wherever you see a y or an f of x. So you get 0 equals x minus 4 squared plus 1. Then you subtract 1 from both sides. I'm just solving using the square root method. Take the square root of both sides and you get x minus 4 is equal to an imaginary number. So since you get an imaginary number here, there's actually no solution. So that's another way to get the answer none. So if you don't have the graph, you can see it by using the equation. Now, how can I use the equation to find a y-intercept? Because it looks like it's a little bit hard to see. See how the y-intercept is going to be somewhere way up here? It's hard to see that from the graph. So how can I find a y-intercept not using the graph? Well, I substitute in 0 wherever I see an x. 0 minus 4 is negative 4. Negative 4 squared is 16. 16 plus 1 is 17. So my y-intercept is going to be 0, 17. Make sure you write it as an ordered pair. Now, the next thing that's the easiest to find is the domain. What's going to be the domain for all your parabolas? Well, it's actually going to be all real numbers every single time, which is pretty nice. So you should always get that credit for those questions. What about the range? The range, you do lowest values to highest values. Nothing. The graph does not get down here. Nothing, nothing, nothing. What's the lowest y value? 1. And what does it go all the way up to? Infinity. Now remember, for the range, it could be open or closed. It's going to be closed because it includes the 1. You actually could get 1 as an output, right? If you plug in 4, you do get 1 as an output. So that's why it's closed on 1. But for increasing, decreasing, and constant, we have to remember that those will always be open and they'll always be x values. So where is this graph increasing? Well, as you go from left to right, where are you rising? From here to here. So what are those x values? That's from 4 to infinity. Always open, always x values. Where's your graph decreasing? Right here. So it goes from negative infinity to what x value? 4. These are the main things I'm going to ask you for. The vertex, the axis of symmetry, whether it's opening up or down. Where is it increasing? Where is it decreasing? What's the domain? What's the range? And are there any x-intercepts? If there are, find them. Are there any y-intercepts? The answer to that is yes. Yes, there will always be a y-intercept on a parabola unless the domain's restricted. And then you have to just make sure you graph it. Now, when you're graphing a parabola, there's actually a nice pattern to notice. When you go 1 away from the vertex, do you see that you rise 1? And when you're 2 away from the vertex, how much do you rise from here to here? You rise 1, 2, 3. Now, let's see how much we would rise on our next interval. Well, we could plug in a 1. 1 minus 4 is negative 3. Negative 3 squared is 9. 9 plus 1 is 10. So I'd be all the way up here at 10. So I go from 5 to 10. That's an increase of 5, a vertical distance. Parabolas are always going to have this nice 1, 3, 5 pattern when the a value here is 1. If the a value is negative 1, it'll still have the nice 1, 3, 5 pattern, but it'll be going in the opposite direction. But if there's a factor here of 2, what you're going to do is you're going to actually multiply these by 2 times 2 times 2, and you'll get your vertical change. So if you don't feel like plugging in all those points, you can use this nice pattern to help you figure out what your graph will look like. When you're graphing a parabola, on an exam especially, you typically want to have at least 5 nice points. So see how this is 1 nice point, 2, 3, 4, 5. Remember, your vertex is h comma k, so you take the opposite of this, keep the sign of this. Well, technically this is just plus 0, so technically it's just negative 1 comma 0. Plot it. Then you want to find your axis of symmetry. Your axis of symmetry is just x equals the x coordinate of your vertex. Always write it as an equation. Then I want you to figure out, does it open up or open down? Well, since this a value is equal to negative 3, that means it's going to open down. So the shape of my graph needs to look like this, with the vertex being negative 1, 0. Now I want to find the domain. The domain is very easy because it's always going to be the same for these problems. It's all real numbers. You can plug in any number you want into this equation and get a real number output. Now, I also want to know the x-intercepts. Well, how do you find the x-intercepts? Well, I can look at the graph right now, and I think it's going to be negative 1, 0. Well, how do I find an x-intercept with an equation? I substitute in 0 for y. So I get 0 equals negative 3 x plus 1 squared. So I'm going to divide both sides by negative 3. And I'm going to take the square root of both sides. So I'm going to get 0 equals x plus 1. And I'm going to get x equals negative 1. So my x-intercept is actually negative 1 comma 0. So for this problem, I actually have one x-intercept. What about the y-intercept? Well, how do I find a y-intercept? I substitute in 0 into the equation wherever I see an x. So this becomes 0 plus 1 is 1. 1 squared is 1. 1 times negative 3 is negative 3. So I get the ordered pair 0, negative 3. Go ahead and plot that. I like to graph my axis of symmetry. That's x equals negative 1. Now I actually already have another point here. I had 0, negative 3, but that means I also have negative 2, negative 3 because of that axis of symmetry. So I'm going to use that axis of symmetry to help me get as many points as I possibly can. I also need to find my range, and I need to find where my graph is increasing and where my graph is decreasing. Notice how the parabolas don't have any piece where it's constant. So typically, when I make my chart, I find a point to the left or right of the vertex. Well, we actually already did. We found 0, right? When we plug in 0, we got negative 3. So now I get to skip that. But now I want at least 5 nice points. So far I have 3. So I need to plug in at least one more point. Most students would choose 1. When you plug in a 1 here, you get 1 plus 1 is 2. 2 squared is 4. 4 times negative 3 is negative 12. So at 1, negative 12, I have another ordered pair, which means I also have 2 away on the other side. I also have negative 3, negative 12. And I go ahead and connect that with a nice smooth curve. Does it match everything I used so far? Yeah, the vertex is negative 1, 0. Axis symmetry is x equals negative 1. It's opening down. This is actually my turning point, so that's a good sign. I have my x-intercept graph. I have my y-intercept graph. Now I just need to find my range. So my range is the lowest value to the highest value. So it stops right there at what y value. Remember, range is talking about the y values. So it goes from negative infinity to 0. Where is this graph increasing? It's increasing from negative infinity to negative 1, and it's decreasing from 1 to infinity. Why is it decreasing from 1 to infinity? Because remember, when you're talking about increasing, decreasing, and constant, you need to give me the x values, not the y values. Now, another quick way to sketch this is to plot your vertex and to use your pattern. Well, typically I said it's a 1, 3, 5 pattern, right? The second difference is 2. But now look what happens when your a value is negative 3. You multiply this by negative 3, multiply this by negative 3, multiply this by negative 3. So remember, as you go 1 away to the right, you go down 3. As you go 1 away to the right again, you go down 9. As you go 1 away on the left, you go down 3. As you go 1 away again, you go down 9. So what would I decrease if I had to do another point? I would decrease 15. So using that pattern is another nice way to get your graph. If not, you can just choose x values to the left or right of your vertex. Can a quadratic function in the form f of x equals negative x plus a quantity squared minus b, where a is any real number. So any real number, which means this is going to be a horizontal shift in either direction, left or right, because it could be positive or negative. B is a positive real number, so that means you're subtracting a positive number. So that's really just like maybe, I don't know, minus 4 or something. Will it ever cross the x-axis? Well, let's see. We have our graph. We would shift it left or right, doesn't matter. And then I see this reflection over here. And then what would this do? Well, it would move my graph down 4 units. So my final graph would be this bolded graph right here, something like that. Will that ever have an x-intercept? Will it ever cross the x-axis? No, it won't. So again, why is that? Because you had a horizontal shift left or right, then you reflected over the x-axis, and this had to be a vertical shift down b units. So no, it will never cross the x-axis. Rewrite this in standard form in graph. So what you really have to do here is use the completing the square method that we've talked about previously. So you're going to rewrite your first two terms, factor out the a value if needed, bring down your constant, leave a space. So now how do you get this first blank? You take b over 2 squared. So negative 4 divided by 2 is negative 2. Negative 2 squared is 4. So you're going to add 4 here. And you have to counteract that. You really did actually add 4, so now you have to counteract that and subtract 4 over here to balance your equation. So now you have to factor this trinomial. It's always going to factor nicely. X minus 2 squared, so it'll always factor as a quantity squared. You designed it to. And you combine your like terms over here. You just rewrote this in standard form or vertex form. Now that you've rewritten it, it should be very easy to be able to find the vertex. So the vertex is just HK, so you take the opposite of this, keep the sign of this. Your axis of symmetry is just x equals the x-coordinate of the vertex. So you get 2, negative 1, and your axis of symmetry is this line. So remember, this point right here needs to be your turning point, so that's very important. Is it going to face up or down? Well, you can look at this a value here, or you can look at the a value in your vertex form. Either way, you're going to realize it opens up. What is the x-intercept or multiple x-intercepts of your graph? So you can write the answer none here. You could have one ordered pair, or you could have two ordered pairs. So let's see for this equation. Well, how do you find the x-intercept? You substitute in 0 for y. So you get 0 equals x minus 2 squared minus 1. So I'm going to add 1 to both sides. And I'm going to take the square root. When I take the square root of 1, I get plus or minus 1. Equals x minus 2. I'm going to add 2 to both sides. So I get 2 plus or minus 1. So 2 plus 1 is 3. 2 minus 1 is 1. So I get the ordered pairs 1, 0, and 3, 0. Whenever I have more than 1, I list it in curly braces. So go ahead and plot those extra points. So that's kind of nice. We have some extra points here. Now let's look for the y-intercept. How do you find a y-intercept? You substitute in 0 into your equation wherever you see an x. So you're going to get 0. 0 minus 2 is negative 2. Negative 2 squared is 4. 4 minus 1 is 3. So you get 0, 3 for your y-intercept. 0, 3. And you notice how you can also have the ordered pair 4, 3 because of your axis of symmetry, 2 away, 2 away. Now you have 5 nice points. You can go ahead and connect them. Does it match what you predicted? Yes, your graph does open up. You have an axis of symmetry at x equals 2, and your vertex is 2, negative 1. So it all kind of matches up nicely. Now if you wanted to make a chart, you could. But the values that I would plug in would have been 1 and 0, but we already have those ordered pairs, so no need to make the chart for this one. Now, how else could we have done it? We could apply the vertex and then use the 1, 3, 5 pattern. Notice how it's 1, and then it's 1, 2, 3. So we actually could have used the 1, 3, 5 pattern here. Why didn't we have to change it or multiply it by anything? Because the a value was just 1. All right, now I need to figure out my domain. The domain is very simple. It's all real numbers. What about the range? You're talking about the y values here. Lowest y value to the highest y value. So it's going to be from negative 1 to infinity. Where's this graph increasing? It's increasing from 2 to infinity. Always open, always x. Where is your graph decreasing? It's decreasing from negative infinity to 2. Always open, always x. Now just a quick comment here. For the y-intercept, do you guys see that it would be a little bit easier to use the original equation here to find the y-intercept? If you plug in a 0 here and a 0 here, you're just left with positive 3. So keep that in mind as you're doing the problems. You don't have to do it a specific way every single time. You don't always have to use this equation. This equation here should be exactly the same as this equation here, but they should look different. They're in different forms, but they are equivalent to each other. So let's see if we can rewrite this in standard or vertex form. So first step when completing the square, we factor out the a value from the first two terms. So when I divide this second term by negative 2, negative 4x divided by a negative 2 equals a positive 2x. Leave your space. close your parentheses, bring down your plus 1, and leave a space. This is the b value that we're going to take half of and then square. So we're going to take half of 2 and square it. So that's why we get a plus 1 here. Did we really just add 1? Well, no, actually, we just subtracted 2, right? Negative 2 times positive 1 is negative 2. So we just subtracted 2. How do I counteract that? I have to add 2 here. So how do I figure that out? I do this times this, and then I do the opposite here. Once I figure that out, I'm going to factor that trinomial. So go ahead and factor that trinomial. Bring down your a value. And then combine your like terms. So this should be exactly the same as this equation right here. Okay, now I need to find the vertex. So it's much easier to find the vertex now that it's in this form. So the vertex is going to be the opposite of this. Keep the sign of this. The axis of symmetry is just x equals the x-coordinate of the vertex. Will this graph open up or open down? You can use either the original equation or your new equation. They'll both tell you that you're going to open down because that a value is less than 0. So your parabola needs to look like this. I want to know the domain. Actually, I want to know the x-intercept. To find the x-intercept of a graph, you substitute in 0 wherever you see a y or an f of x. So you get 0 equals negative 2 x plus 1 squared plus 3. I'm going to subtract 3 from both sides. And I'm going to divide both sides by a negative 2. So negative 3 divided by negative 2 is 3/2. Then I'm going to take the square root of each piece. So I'm going to get x plus 1 is equal to plus or minus the square root of 3 over the square root of 2. Don't forget to rationalize this by multiplying by square root of 2 over square root of 2. So you get x equals, subtract 1 from both sides, plus or minus the square root of 3 times 2 is 6 over 2. So you're going to get 2 ordered pairs for your x-intercept. You get negative 1 minus root 6 over 2 comma 0, negative 1 plus root 6 over 2 comma 0. Whenever you have more than 1, you just list it in roster form and put the curly braces around it. To find the y-intercept, you're going to substitute in 0 wherever you see an x. Again, you can use this equation, but do you see how it's much easier using this one? When you plug in 0, you get 1. So 0 comma 1 is your x-intercept. Now, when you go to plot this graph, I want you to plot your vertex first, negative 1 comma 3. You can plot your axis of symmetry with a dashed line, so you know it's not part of your graph. And you can plug a point to the right. So if you plug a point to the right, you'd be plugging in 0. You already have that point. Then you can reflect it over the line of symmetry. Now, what if I wanted another point? Well, I could plug in a 1. So when I plug in a 1, I can either plug it into this equation or this equation. I also get the same answer. So when I plug in a 1, I get 1 plus 1 is 2. 2 squared is 4. 4 times negative 2 is negative 8. Negative 8 plus 3 is negative 5. So 1, negative 5, I should be down here, which means I can reflect it over and also get the point negative 3, negative 5. This is good because it's matching what I predicted over here with the graph facing down. Now, do you see that these x-intercepts here do not hit nice points? Well, that's because they were irrational. Notice how you still get 2 ordered pairs, but they're irrational, so they're a little bit more challenging to graph. But when you graph, you should make sure that you have 2 x-intercepts, right? If you get 2 using the equation, you should have 2 on the graph. Now, if I wanted to graph this using the pattern, I would do negative 1 comma 3. Plot that first, and then I get the 1, 3, 5 pattern and use my a value. So this would be times negative 2 times negative 2 times negative 2. So this is a vertical change of 2. This is a vertical change of 1, 2, 3, 4, 5, 6. So you can see how it matches the pattern we predicted. What's the domain of this graph? Well, again, it's going to be all real numbers. So you should always get that right. Your range is going to be lowest y value to the highest y value. And it actually hits 3, so that's why it's included with a closed bracket. Where is this graph increasing? So the graph is increasing from here to here. So that's from negative infinity to negative 1. Always use x values, always open. Decreasing from -1 to positive infinity.